Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The unfolding history of black holes. The history of black holes, a concept that has captured the imagination of physicists and astronomers for centuries, begins with the intersection of mathematics and natural philosophy. The idea that light itself could be influenced by gravity first emerged in the late 18th century, well before the term black hole was ever coined. In 1784, English clergyman and natural philosopher John Michell proposed a revolutionary idea in a letter to the Royal Society of London. Michell suggested that a sufficiently massive star could possess a gravitational pull so intense that even light could not escape its surface. This theoretical construct, which Michell called a dark star, relied on Newtonian mechanics and the corpuscular theory of light, which imagined light as a stream of particles. In the same era, French mathematician Pierre-Simon Laplace independently developed a similar notion. Laplace included the idea of dark stars in early editions of his book Exposition du Système du Monde, though he later removed it, possibly due to the lack of empirical evidence and its speculative nature. Michel's and Laplace's ideas, while intriguing, faded into obscurity as the wave theory of light gained prominence in the 19th century, casting doubt on the notion of light being influenced by gravity. The advent of Einstein's general theory of relativity in 1915 reignited the discussion of gravitational phenomena at extreme scales. Einstein's equations revolutionized the understanding of gravity, describing it not as a force acting at a distance but as the curvature of spacetime caused by mass and energy. In 1916, Karl Schwarzschild, a German physicist, provided the first exact solution to Einstein's field equations. Schwarzschild's work described the gravitational field around a spherically symmetric, non-rotating mass. His solution revealed a critical radius, later known as the Schwarzschild radius, beyond which nothing, not even light, could escape. Though Schwarzschild's work was a mathematical breakthrough, the idea of such objects being physically real was still considered highly speculative. The concept of objects collapsing under their own gravity took a more concrete form in the 1930s with the work of Indian-American astrophysicist Subrahmanyan Chandrasekhar. He demonstrated that stars above a certain mass limit, now known as the Chandrasekhar limit, would not remain stable as white dwarfs after exhausting their nuclear fuel. Instead, they would collapse under their own gravity. Around the same time, theoretical physicist Robert Oppenheimer and his student Hartland Snyder explored the idea of gravitational collapse in detail. Their calculations showed that a sufficiently massive star could undergo a runaway collapse, forming what we now recognize as a black hole. Despite these advances, the term black hole had yet to be introduced, and such objects were often regarded as theoretical oddities rather than real celestial phenomena. The term black hole itself was popularized in the 1960s by American physicist John Archibald Wheeler, who brought clarity and focus to the study of these enigmatic objects. By then, observational astronomy had advanced to the point where indirect evidence of black holes could be pursued. The discovery of pulsars in 1967 by Jocelyn Bell Burnell and Anthony Hewish lent credibility to the idea of compact objects resulting from stellar collapse. Pulsars, which are rapidly rotating neutron stars, demonstrated that the remnants of massive stars could exist in extreme states. As black holes move from theoretical constructs to astrophysical objects of interest, their properties were further explored through Einstein's equations and quantum mechanics. By the late 20th century, astronomers began to detect compelling evidence for black holes, particularly in binary star systems where a visible star's motion suggested the presence of an unseen, highly massive companion. The first such system, Cygnus X1, was identified in the 1970s, marking a milestone in the observational confirmation of black holes. The history of black holes, therefore, is one of theoretical prediction evolving into empirical discovery, driven by the convergence of mathematics, physics, and astronomy. The gradual transition from black holes as abstract theoretical objects to observable phenomena marked a transformative era in modern astrophysics. Following the theoretical groundwork laid by early 20th century physicists, the second half of the century witnessed a surge of interest in understanding black holes as real entities shaping the dynamics of the cosmos. This period saw the development of advanced observational techniques, further refinement of theoretical models, and the advent of computer simulations that allowed scientists to probe the behavior of matter and energy in the extreme environments surrounding these enigmatic objects. One of the major breakthroughs came in the study of compact objects in binary systems. When a massive star collapses into a black hole, it often remains gravitationally bound to a companion star, forming a binary system. If the companion star is close enough, its outer layers can be drawn toward the black hole's intense gravitational pull, forming an accretion disk. This swirling disk of superheated gas emits high-energy radiation, particularly in the X-ray spectrum, as the matter spirals inward before crossing the event horizon. Observations of these X-ray emissions provided the first indirect evidence for the existence of stellar mass black holes. Cygnus X1, discovered in the early 1970s, became one of the first and most studied candidates for a black hole. The system consisted of a massive blue supergiant star and an unseen companion emitting powerful X-rays. Detailed measurements of the system's orbital dynamics indicated that the mass of the unseen companion exceeded the upper limit for a neutron star, leaving a black hole as the most plausible explanation. This discovery not only confirmed the theoretical predictions of stellar collapse but also solidified the notion that black holes were more than mere mathematical curiosities. Around the same time, advancements in radio astronomy opened new windows into the universe, revealing the existence of quasars, extraordinarily luminous objects at the centers of distant galaxies. Quasars were later identified as powered by supermassive black holes, objects with masses millions to billions of times that of the Sun. These black holes reside at the cores of galaxies, where they consume surrounding gas, dust, and even stars, releasing immense energy in the process. The connection between supermassive black holes and galaxy formation emerged as a central theme in astrophysics, suggesting that these objects play a crucial role in shaping the structure and evolution of galaxies. Theoretical advances during this period also deepened the understanding of black hole physics. Stephen Hawking, one of the most prominent physicists of the 20th century, revolutionized the field with his groundbreaking work on black hole thermodynamics. In the 1970s, Hawking demonstrated that black holes are not completely black but emit radiation due to quantum mechanical effects near the event horizon. This phenomenon, now known as Hawking radiation, revealed a profound link between gravity, quantum mechanics, and thermodynamics, suggesting that black holes could eventually evaporate over immense timescales. Hawking's work highlighted the deep and often paradoxical connections between the largest and smallest scales in the universe, sparking debates that continue to this day. In parallel with these theoretical developments, observational techniques continued to improve. The Hubble Space Telescope, launched in 1990, played a pivotal role in identifying supermassive black holes in the centers of nearby galaxies. By measuring the motions of stars and gas near galactic cores, astronomers were able to infer the presence of central objects with masses far exceeding those of any known star clusters. These findings provided compelling evidence that supermassive black holes were not just theoretical constructs but fundamental components of galactic systems. As the study of black holes expanded, the development of numerical simulations allowed scientists to model the complex interactions between black holes and their environments. These simulations provided insights into phenomena such as accretion disk dynamics, jet formation, and mergers between black holes, predicting the gravitational wave signals that such events would produce. These predictions laid the groundwork for one of the most significant scientific achievements of the 21st century, the direct detection of gravitational waves. The modern era of black hole research represents a triumph of human ingenuity and technology, as it has become possible not only to infer the existence of these mysterious objects but also to observe their effects directly. This final phase of the history of black holes is characterized by groundbreaking discoveries, unprecedented observational capabilities, and the profound implications these findings have for our understanding of the universe. A monumental leap forward occurred on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, ripples in spacetime predicted by Einstein a century earlier. These waves were produced by the merger of two stellar mass black holes approximately 1.3 billion light-years away. This historic detection confirmed not only the existence of binary black hole systems but also the ability of these objects to merge and release energy on a scale unparalleled in the cosmos. The detection of gravitational waves opened a new window into the universe, allowing scientists to listen to cosmic events and study black holes in a way that had never been possible before. In subsequent years, the gravitational wave observatories LIGO and Virgo detected dozens of black hole mergers, revealing an unexpected diversity in their masses and spins. These observations raised new questions about the formation and evolution of black holes, particularly those that seem to lie outside the expected mass ranges predicted by stellar evolution models. Meanwhile, plans for next-generation observatories such as the Laser Interferometer Space Antenna, LISA, promise to extend the detection of gravitational waves to even larger scales, including mergers involving supermassive black holes. Perhaps the most visually striking milestone in black hole research came in April 2019, when the Event Horizon Telescope (EHT) collaboration released the first-ever image of a black hole's event horizon. This remarkable image captured the silhouette of the supermassive black hole at the center of the galaxy M87, located some 55 million light-years away. The dark shadow, surrounded by a glowing ring of light, matched theoretical predictions of how light would be bent and trapped by the immense gravitational pull of a black hole. This direct observation of a black hole's shadow was a technological and scientific feat, combining data from a network of radio telescopes across the globe to achieve an unprecedented level of resolution. Building on this success, the EHT collaboration released further observations in 2022, unveiling an image of the supermassive black hole Sagittarius A at the center of our own Milky Way galaxy. Although smaller and more dynamic than the black hole in M87, Sagittarius A offered another opportunity to test the predictions of general relativity and study the behavior of matter near an event horizon. These images provided tangible evidence of the existence of supermassive black holes and underscored their role as cosmic powerhouses shaping the structure and dynamics of galaxies. The study of black holes continues to push the boundaries of physics, posing profound challenges to our understanding of space, time, and matter. One of the most tantalizing questions involves the nature of singularities, the theoretical points of infinite density and zero volume at the centers of black holes. The existence of singularities suggests a breakdown of classical physics, pointing to the need for a unified theory of quantum gravity. The study of black holes has become a testing ground for some of the most ambitious theories in physics, including string theory and loop quantum gravity. Moreover, the role of black holes in the cosmic ecosystem has emerged as a central theme in astrophysics. Supermassive black holes are now understood to influence their host galaxies through feedback processes, such as powerful jets and winds that regulate star formation. These interactions have far-reaching implications for the growth of galaxies and the large-scale structure of the universe. Meanwhile, the discovery of intermediate-mass black holes, which bridge the gap between stellar mass and supermassive black holes, has provided new insights into the formation pathways of these enigmatic objects. The history of black holes is far from complete. New observatories, such as the James Webb Space Telescope and the upcoming LISA mission, promise to unveil even more about the nature of these objects, from their formation in the early universe to their role in shaping cosmic evolution. The ongoing search for primordial black holes, hypothetical remnants of the Big Bang, may shed light on dark matter, one of the greatest mysteries in modern cosmology. As humanity continues to explore the cosmos, black holes remain at the forefront of scientific discovery. They challenge our understanding of the universe's fundamental laws, serve as laboratories for extreme physics, and inspire a sense of wonder about the infinite complexities of the cosmos. From their origins as mathematical curiosities to their current status as observable and profoundly influential phenomena, black holes have become one of the most captivating and transformative subjects in the history of science.